also do games for other companies. So I think Sea of Thieves is one of the ones that you've probably heard of.
Yes, sir.
So yeah, so they've written a series of C++ programming courses that are introductions for Unreal Engine. They've been running these courses all week. So this is the last one in the series. So this one is an introduction to AI for Unreal Engine. So I am going to just introduce Carlos, and I'm going to be very quiet. What I should tell you is if you do want to ask any questions, we sent you a link to a question pro. And what we're going to do is we're going to collate all those questions, get the answers and send them out afterwards. So please do, you know, send in your questions via the question pro. So I'm going to hand over to Carlos now.
Thank you. So hi guys. I'm sure some of you have seen me in over the last week, but my name is Carlos Diabru, and I'm a senior engineer here at Flix Interactive. We are an Unreal specialist studio. That being that we primarily focus on games being built in the Unreal Engine. As Carrie mentioned, we've worked on titles such as Sea of Thieves, Crackdown 3 as well, which have been made in the Unreal Engine. All of these projects have taken um, part in many versions of the engine, so we've been lucky to have experienced a lot of them over our time working on the Unreal Engine. So I'm just going to share my screen and start my camera for you guys. There we go. So today we're going to be going over the AI in Unreal Engine. So in this talk, we're going to look to cover the main tools that programmers can utilize to build AI in the Unreal Engine 5. That being, we're going to cover the AI controller, behavior trees on the blackboard, as well as the navigation mesh, the environment query system, or usually called the EQS. We're also going to be covering AI perception, as well as some of the newer tools that have been made available in Unreal 5, such as smart objects, state trees, the mass entity system, and lastly, the zone graph. So we can begin with the AI controller, as it's actually a really key part of everything that we do within AI. A controller in UE5 is a non-physical actor that can possess a pawn or a derived actor from pawn, such as, for example, a character. It's built into UE5 already, and we have several derived types of controllers, such as the one that we're discussing right now. But it's actually also worth mentioning the player controller, just so we can contrast between difference between the two. The player controller can be best described as the will of the player. So we can summarize here and assume that basically the AI controller will be our simulated will that controls our AI agent. All controllers, no matter what type, share some common traits and functionality. The first is that the control of the pawn is actually done in a function called the onPossess function. And relinquishing control of that pawn is done via the onPossess function available to us programmers. Controllers also have a one-to-one relationship with a pawn, meaning that a single pawn can only have one controller, which works perfectly for most AI. However, where the AI controller kind of differs from the base controller and even the derived version for the players, the player controller, is that it's actually exclusive created on a server. It's never going to be replicated to any of the clients in a networked game. This is super important as AI must be authoritative and in networked games, the server will be our source of truth at all times. As well as this, the AI controller also houses some components that are key to making our AIs function in the game. These components are as follow. We have the behavior tree component, which can be best described as the brain of the AI. We also have the blackboard component, and this can be described as the memory of our AI. We also have the perception component, which, as the name suggests, describes essentially what senses the AI can perceive. And last but not least is the path following component. Again, self-explanatory in the name, it will basically allow our AI to navigate through the level. However, we will be covering these components in more details in the following slides. So previously, in the Unreal Engine, triggering AI logic used to be done either through blueprint or through code by starting the behavior tree when processing the pawn. However, the AI controller now actually exposes control in Blueprint and in C++ to just allow the AI logic to just immediately begin when we process that pawn. The AI controller also implements the generic team agent interface. This interface implements a functionality that allows us to query what team the AI agent is on, as well as their attitude towards another actor in the game. Unreal 5 implements a generic team identification system out of the box, which is flexible and completely up to each developer to implement in whichever way they wish to. The reason for this is that many games want to drive target selection logic as well as any other logic based on what that game might be. An RPG might select targets in a different way altogether than, say, for example, a shooter AI. So the AI controller also provides programmers with a handy entry function to determine how our AI agent may actually select that focus. The actor's perception updated function sends through an array of what's currently being perceived. Again, the implementation of this is left empty to allow each developer to implement their own target selection process. So now that we know what simulates the will of our AI agents, it's time to look at what drives the logic and memory of the AI agent, and that is our behavior tree and blackboard. The behavior tree can be best described as the brain of the AI. In fact, the behavior tree component itself actually inherits from the brain component inside the engine. The behavior tree component is held by the AI controller, and it actually makes a clear assumption that its owner is always an AI controller, with functions such as get AI owner being made available to engineers and developers in Blueprint. It's also strongly paired with a Blackboard component, exposing functions to programmers and developers through Blueprint that allows us to retrieve that Blackboard component from the behavior tree directly. It is important to note that although this ownership pairing has been established in the code architecture, the AI controller does not come with that brain component already attached to it. This can be done by the developer themselves through Blueprint or C++. But lastly, if you choose to add the behavior tree component through Blueprint or through C++, the AI controller will automatically search for the brain component on itself and set its member variable when it's created in the world. The behavior tree component allows developers to plug in a desired behavior tree inside the editor. So if you already add it through C++ or inside the editor, you'll be able to plug this in straight away. This will basically mean that it will be run immediately when the AI processes the pawn. Alternatively, we can also explicitly just call the run behavior tree function and just pass it through the specific tree that we want to run, as and when we find it suitable. If a behavior tree component is not present when we call the run behavior tree, then one will be created for you inside the code. The behavior tree component is in charge of running our AI logic, that being the behavior tree asset itself. As already mentioned, it will start that AI logic when we possess, and it will stop that AI logic when we unpossess the pawn. The behavior tree component will also tick our behavior tree and can also then pause it if we wanted to. The brain component of the AI also features a special messaging system that allows that the AI logic can utilize. So you'll find examples of these sort of messages already in the engine. These messages basically allows us to know what may have gone on during the process of our AI logic. For example, in the move to task, we can determine whether we succeeded or failed our move, which will determine essentially how we proceed to the next node in the tree, or actually fail the node in question altogether. Now, a behavior tree allows an AI agent to essentially do their own thinking and make decisions that drive their functionality. A behavior tree can be paired with a blackboard to efficiently make those decisions, although it isn't necessarily needed to have one to actually drive your logic. However, we do recommend that you do, as it is an efficient way of storing information at runtime. As we have previously discussed, behavior trees have been strongly paired with a blackboard in code. So it's pretty handy and already there available for you. Behavior trees can be created within the editor, as can be seen in the images below. We simply right-click into the content browser, go down to the artificial intelligence section, and just select the behavior tree option. Behavior trees are built in a hierarchical set of nodes that control the flow of our decision making. We're going to cover this decision making shortly. In the Unreal Engine, behavior trees are event driven, which avoids doing unnecessary work every frame. The behavior tree passively listens for events that can then be used to trigger changes in that tree. This type of architecture means that the code does not need to iterate over the entire tree every tick. Instead, we just rely on those messages to inform us of changes that may have happened. This also helps with debugging behavior trees, as we simply only show the relevant information at the time that it's being executed. So here we have an example of a behavior tree in which the AI agent can either move towards the player and attack them, or if they have not perceived the player, then they will patrol randomly until they can perceive that player. Behavior tree branches are executed in order. So when authoring your behavior tree, you will notice that all the nodes in the behavior tree have a number assigned to them when they're placed within the graph. This numerical value tells us the order in which these nodes will be executed in. So at the higher level, the behavior tree executes from top to bottom, whilst at the branch level, we will execute from left to right. This is critical to understand when authoring your behavior trees. You wouldn't want an AI agent, for example, to prefer patrolling to chasing and engaging with the player. It's also important to understand that nodes in the behavior tree can be moved around and will then also update their execution order based on the position that they are in. So a clean and well spaced out behavior tree is a must. In the example that we have here on the screen, we check whether we have perceived the player and execute the branch if we have. Otherwise, we're just going to fall into the second part of the tree and just patrol instead. Now, behavior trees bring with them their own editor graph, as we have seen just in the previous slide. And now it's actually time to look at those nodes and how they make up our behavior tree. In Unreal, behavior trees have 5 types of nodes. The first of them is the root node. We also have composite nodes, task nodes, decorator nodes, and also service nodes. So let's take a look at what each of these are. Now, the root node is our default node that is found in all behavior trees. It serves as the starting point for the behavior tree, and thus it cannot be deleted. It's also a unique node within the tree, and it has a few special rules around it. A root node can only have one connection. If the connection to the root node is removed, then the entire tree is disabled. It does not support attaching of decorators or service nodes onto that root component. Lastly, the root node does not have any inherent properties of its own. However, when you select the root node itself, it will show you the properties of the behavior tree that you're working in. As we can see in the example below, selecting the root node allows us to set the behavior tree's blackboard, as you can see there. So now that we have a root node, it doesn't really do a whole lot. But this is where composite nodes come in. Composite nodes define the root of a branch. As well as this, they determine the rules for how that branch is executed. We will see how each type defines how it's executed, and we'll learn more about them in the following slides. Another important thing to note about composite nodes is that they are the only type of node that can be attached to a root node. Composite nodes support both decorators and service nodes. Decorators allows us to control how we enter that branch, or even actually cancel out of that branch mid-execution. Service nodes will only ever be active if the children of the composite node are being executed. This is important to understand when you come to placing your service nodes in your trees. There are three types of composite nodes that we can make use of in the Unreal Engine, that being the selector, the sequence, or a simple parallel. So let's find out about how each of these differ and what they offer to us to achieve our logic. So we'll start with the selector node. This will execute its children from left to right. It will stop executing when one of its children fail. If a child succeeds, then that selector node itself will succeed. However, if all of its children fail, then that selector node will fail. We can see here on the example on the right that the selector node will attempt to execute the first wait task. However, its decorator will cause it to fail after about a second of execution, and thus it will fail that task. Instead of failing straight away, the selector node will execute the secondary wait task and then succeed. If we were to place the secondary task ahead of the first, for example, then we would actually see that the first task would succeed and the second one would never be run. On the image on the left, we can see that the composite nodes also expose out two variables to developers. The first is the apply decorator scope boolean. If this is set, all decorators in the branch below will be removed when the execution flow leaves the branch. However, the decorators on that specific node itself will not be affected by this. Lastly, we also have the node name, and this will basically be the name that the node will display in the behavior tree graph itself. It's usually a really good idea to give your composite nodes a name, as this will act as a way to identify what that branch of your behavior tree is doing. And this is especially useful for when you have behavior trees that grow quite large in size. So moving on to the composite nodes. Sequence nodes. Sequences also execute their children from left to right. Sequence nodes will stop executing when one of its children fail. So if a child fails, that sequence will fail itself. If all of the sequence's children succeed, then that sequence will also succeed. In the example that we have on the right, we can see that we just have three wait tasks, with each executing one after another. Now, if we were to take our example from before, and we apply a similar condition to any of those task nodes, like we did in the selector example, we would actually see that the sequence will then immediately fail when it hit that task. And it would not execute any of its children that follow that task that failed. Sequences are ideal for things such as, for example, moving towards your target, as we would likely run some sort of environment query to find a location to move to, and then proceed to move to that location. On the left, we have a similar set of properties that we saw in our selector node, and they do exactly the same thing. So lastly, with the composite nodes, we have the simple parallel. The simple parallel node allows a single main task node to be executed alongside a full tree. When the main task finishes, depending on what finish mode you have selected, the other tree will either be aborted immediately, or we will delay until that tree finishes as well. Simple parallel nodes are great for things such as moving continuously while shooting, for example. So onto decorator nodes. Now, decorator nodes can be attached to either composite or task nodes, but they cannot be placed on the tree on their own. They define whether a node or branch can be executed. They are also known as conditionals in other behavior tree systems. Lastly, decorators can be used as a way to abort parts of a behavior tree. We can actually jump into the engine and take a look at an example of this that's already available within the Lyra game that we provide. So we can first begin to look at how it actually looks inside the engine. When we click on our Have Ammo decorator node that we have here, we'll see that we have a couple of options available to us in here in the details panel. So, under the Blackboard heading, in the middle, we can see the following controls. We can see a key query. Now, in our case, this is not set, but we can easily change it to an is set instead. So we can, in our case, we can, in this case, if we set it to is set, we can say only come into this branch if we have an enemy set on our Blackboard. The other option is not set, that would do essentially the opposite. So in this case, what we're saying to the behavior tree is that please come in here whenever our out of ammo is not set. Whenever we run out of ammo, we will set that value in the Blackboard and we will stop running this part of the behavior tree. Next, we have the Blackboard key. And this is basically the key that we will look to examine to see if it has been set or not set, as it may be the case. Next, we can look at the flow control heading, which has two important fields. The first is the notify observer, and this has two options that we can control. We can see that it either has an on value change or an on result change. The on result change will mean that we will only reevaluate the condition when the condition has been changed. So in our case, this would be if whether the value has been set or not set. The on value change will only reevaluate when the observed Blackboard key has been changed itself. So essentially, whenever then any changes happen to it, we will react to that. We also have a observer abort option here, and this has four available options to us, with none, self, lower priority, or both being the options that we have here. So with none, this is just a default that will come with most decorators. And it basically means that it will not abort any part of the tree. Self will essentially say to the behavior tree that this will abort this node and any subtrees running under that node. If we select the lower priority option, then this will basically abort any nodes to the right of this node. Remember that behavior trees run from top to bottom and left to right at the branch level. So anything to the right of our given node will be regarded as lower priority. Lastly, we also have the both option, and this will basically do the same as self and lower priority together. It will abort every part of the behavior tree. We can actually see these things and how they work by actually some clever debugging that, built into the editor. We can see that if we select self, for example, our right part of the tree is no longer lit up. This will basically tell us that any lit up parts within our behavior tree will be aborted. If we were to set this to lower priority, we now see that the highlighting on the left is gone, and the right-hand side now will be aborted. And if we select both, we now see that everything for our behavior tree will now be aborted. Unreal comes with a choice of decorators that we can make use of. If you'd like to see what these are, then we can provide a link as well at the end of the presentation. However, if you find that none of these decorators meet your needs, you can actually also create your own decorators either in Blueprint or in native C++. We can actually see the option already available to us here in the editor. We have a shiny new decorator key, which you can just click and it will create our new decorator for us in Blueprint. So we can now move on to our task nodes. Now, task nodes are essentially nodes that will do something. For example, this can be to move our AI agent or edit a Blackboard key that we have somewhere in our Blackboard. Tasks nodes also support decorators and services as part of their behavior. Other than composite nodes, task nodes are the only other node type that can be placed down on the behavior tree graph itself. Now, there is a wide choice of tasks already implemented in the Unreal Engine, one of which we can see in the example below, that being the move to task. Once again, with decorator nodes, you can create your own tasks within Blueprint or C++ as you wish. So lastly, we come to the service nodes. Now, service nodes are nodes that will execute at a defined frequency when their branch is being executed. Service nodes can be used to perform checks or even update data about the world that can then be used. They can be used in place of parallel nodes that you might see otherwise in other behavior tree systems. Now, the Unreal Engine comes with two services supported out of the box. The first is a default focus service, which will set the focus actor directly to the AI controller. This can be especially useful for getting hold of said actor in Blueprint or C++ instead of having to access that data directly from the Blackboard. The second supported service in the Unreal Engine is a run EQS service. This service can be used to regularly run an environment query system template at an assigned interval and will then update a given Blackboard key with that result. Lastly, and it's really important to note this, is that although services can tick as part of their assigned frequency, you don't actually have to use them as such. Services actually also come with two functions that allows us developers to know when a service has come into relevancy of the tree or when it has actually ceased to be relevant. And what we mean by those is that whenever our nodes underneath the service are being executed, we will know when that begins. And whenever the branch completes or is aborted, we will also know when that happens, and we can hook onto those functions. So now that we know all about the different types of nodes, we should discuss how we can actually utilize memory within the behavior tree. Now, behavior tree nodes exist as shared objects, meaning that all AI agents using the same behavior tree will actually share the same exact single set of nodes instances. This approach has a twofold effect. So the first is that it improves CPU performance. And secondly, it also reduces memory usage for that behavior tree. It does, however, come with a caveat. Because they're shared nodes, they cannot store specific agent data. However, if we do find ourselves needing to store specific agent data, Unreal does actually support that ability in 3 different ways. So let's cover the first way which we can do so. And that is to essentially instance that node. Behavior tree nodes expose a Boolean to developers that allows us to instance the node, and that is the bCreateNode instance Boolean. If this is set to true, then this will grant each AI agent using that behavior tree a unique instance of that node. This will, of course, then allow us to store specific agent data, but it does come at the cost of performance and some memory usage. There are examples of these nodes already in place in Unreal's own implemented set of nodes, such as, for example, the play animation node or the run behavior tree dynamic node. So what if we don't want to instance our nodes? Well, the second way that we can actually get around storing specific agent data will be to actually just use the Blackboard storage. The Blackboard storage can be accessed within nodes to get that agent-specific data. Key functions in our nodes are actually already sent through the AI agent's behavior tree component as one of the parameters that get passed to us. As developers, we can simply expose some sort of fname property or make use of the Blackboard key selector property to then allow us to get and set data from the Blackboard at will. It is important to note that this approach will only support Blackboard data types, which we'll actually discuss shortly. And lastly, we come to node memory. Unreal allows developers to create custom struct or classes to store variables inside that node memory. Many of the functions in the behavior tree node pass through an uint8 pointer as a parameter, alongside that behavior tree component that we spoke about previously. This parameter will indicate the block of memory that has been allocated to that AI agent. In order to take advantage of the node memory, we must first implement a function called getInstanceMemorySize function. Now, this must be implemented if we're using this approach, as it will actually dictate the size of the memory block that we need for that node. Nodes will allocate that this amount of memory for each AI agent that uses the behavior tree. Node memory is stored as a single contiguous block to optimize performance. However, it is very important to keep in mind that node memory is not part of the UObject ecosystem. So our memory is not going to be visible to the garbage collector. It's highly recommended that when we're dealing with reflection types, that we make use of the tweak object pointer to hold our variables. We can actually see an example of this below. This example was actually lifted from the move to task that's already implemented inside the Unreal Engine. So now that we've covered the simulated wheel of the AI as well as the brains of the AI, we can actually then begin to discuss the memory of the AI. The Blackboard is a special asset type that is created specifically to work in conjunction with behavior trees. It is used to store information in the shape of Blackboard keys. This information can then be queried by the behavior tree at runtime to make those informed decisions. A Blackboard can hold up to 255 entries. Blackboard data also supports parent Blackboards. This means that we can inherit keys from another Blackboard. So if you're building your AI and you have, say, multiple types of AI, such as, for example, maybe NPCs, humanoid NPCs versus wildlife, and maybe even monster AI, you might actually find that they share a common set of properties or within them. You can actually then just extrapolate that into a parent Blackboard that they can all share as part of their own set of Blackboards. And that would just basically mean that those shared pieces of data can then just be there for us to use. Now, the Blackboard component offers us programmers the entryway for querying and saving data from and to the Blackboard respectively. The Blackboard component is also strongly paired to the behavior tree component. It will actually cache that component, and programmers can retrieve the brain component of the AI directly from the Blackboard. The Blackboard component also follows a similar pattern to the behavior tree component in terms of its creation. It's not actually present by default on the AI controller, and much like the behavior tree component, it can be added either via Blueprint or C++. However, this isn't necessary, as one will be created when the AI logic is triggered to start. It's also important to note that a Blackboard is not essential in the running of AI logic. it just helps you out. Again, much like the behavior tree component, the Blackboard component does expose a Blackboard asset to the editor that can be then plugged in. The Blackboard component also offers a unique callback functionality that allows objects to register as observers of a particular Blackboard key. That means that they can then be notified when that Blackboard value has been changed. Examples of this can already be found in the engine, such as the move to task, which registers with the Blackboard component to get notified when the Blackboard in question has changed. I can actually jump into the code very, very quickly and take a look at this. We can actually see on line 68 here that we will sign up a delegate handle stored within the memory of this node so that we can register as an observer to a Blackboard key. This will basically then fire our on Blackboard value change function that we've already assigned to that delegate. And voila, we're now registered as an observer to that specific Blackboard key. This is a handy pattern if you wish to allow, for example, your AI to pivot based on changes in the world as it executes its task at hand. Now, a Blackboard can store the following data types. We can store vectors and rotators, as well as bools, ints, floats, as well as new classes and new objects themselves, alongside f names, enums, and strings. If you wish to look at how that data for each key is manipulated, then please look at the Blackboard key all types header inside the engine, which gives us a handy include for all of the listed types above. Lastly, it is important to note that a Blackboard cannot store arrays of data. The Blackboard works off a single block of memory, and data types that are stored with offsets based on their data size. So it's now time to look at how we can make our AI agents traverse the world as they perform their behaviors. The Unreal Engine 5 comes with a system that supports land-based AI movement out of the box, and that is our navigation mesh. Now, Pawn is the base processable class that the Unreal Engine offers, but it is not assumed to be a humanoid entity, whereas Character is the first derived version of Pawn that will make an assumption of a vertically aligned humanoid entity. It is primarily these entities that make use of the navigation system. Now, the navigation mesh is generated within the editor. Queries, when we generate this now our navigation mesh, it will query the environment on generation to understand where the AI can traverse and which areas may have been marked as non-navigable. It is built specifically for land-based AI, and it can support either a static version of a nav mesh or a dynamic version of that nav mesh. Navigation modifiers volumes can also then be used in our levels to apply a navigation cost to our navigation mesh, or actually even at points just entirely block an area of space. Physical objects that are placed in the world can control whether they actually affect that navigation mesh or not. So this is really, really key when you're working with level art, for example. Different navigation data can be built for different AI agents who would wish to have that level of support. Whenever we're in the editor, we can actually hit the P button, which is the default binding, to visualize our navigation mesh that has been placed inside the level. Navigation links can also then be placed on the level and form basically a link between navigation mesh edges to allow the AI to traverse that space where there may not be a navigation mesh for them to actually do so. Now, the navigation mesh is generated within the editor. It does not come built into any level within Unreal. In order to generate a navigation mesh, we must first drop a navigation mesh bound volume inside the level. This can be found in the Place Actor window under the Volumes section. We can then resize our volume to cover the area that we wish to have navigation mesh on. In order to know if your navigation mesh has been generated correctly, we can just then hit that P key that I spoke about earlier when we're not actively playing inside the editor. And that will basically allow us to visualize that navigation mesh if it has been generated correctly. So in the picture on the right, we can see that we have some controls over our navigation mesh once it has been generated inside the level. For example, we can control the max slope angle that this navigation mesh will support. Another key parameter to control with navigation meshes is whether their runtime generation is either static or dynamic. Now, static will of course be a cheaper version of these two. However, it is important to note that it's important to understand what your project needs may be. If we have a completely static scene, then a static generation mesh is perfect. But if your game has an ever-changing scene, such as trees falling over or objects that are being built at runtime, then a dynamic version of navigation mesh will be required. Lastly, it is important to understand that physical objects placed within the world will individually control whether they affect that navigation mesh or not. So ensuring that these are set up correctly is also really key to authoring your navigation meshes. So in the picture that we have here on the screen, we can see that we've generated a navigation mesh around this little level. We can see, for example, that the tables and chairs in the middle of our level will affect the navigation mesh. That allows the AI to basically reason that they cannot traverse that particular area of the level. The navigation mesh system in Unreal supports different navigation meshes for different AI agents. As can be seen in the image above, we can define a humanoid profile that supports AI agents of a specific radius and height. We can also determine other aspects of the navigation mesh generation. This will allow us to support different agents with appropriate navigation meshes for them to use. A larger AI agent may not be able to navigate through those narrow spaces in the terrain, so therefore the navigation mesh should not allow them to do so. As we mentioned a few slides back, we can also make use of navigation link proxies and navigation modifiers that can then affect how AI can traverse that environment. With navigation link proxies, as the name suggests, basically allows us to find links between gaps in the navigation mesh. An AI agent can then utilize these links to temporarily leave that navigation mesh. So in the example that we have here on the screen, the AI agent can make use of that navigation link to jump off the ledge to get down to the bottom part of the level. It's also really important to note that with navigation link proxies, we can actually control the flow of that link. So for example, in this case, we've set to the AI that they can only use this link to jump down onto the ledge, but they can never use it to go from below up to the ledge. As well as linking the navigation messages together, we can utilize navigation modifiers to affect navigation in several ways. With navigation modifiers, we can do some of the following. We can actually block navigation entirely. This will basically create a void in the void of navigation in a desired area, meaning the AI will be forced to move around it instead. But equally, we can also affect the cost of navigation. We can affect the cost of either moving through that section or actually just even entering that section. In the image that we can see here, we have defined an area by the wall that will not be desirable for the AI to choose. However, if it must, it will traverse that area to get to its goal location. We can leverage this to create immersive experiences for the player, where the AI can be seen to cleverly choose other ways of getting to the player that avoid choke points like this. So now that we know the genetic makeup of our AI agent, and we can now actually achieve navigation through our levels, we can take a look at how our AI agent will be able to query the world for information. And this is where the environment query system comes in. The environment query system is a feature within Unreal that is used to gather data about that environment. An example use of this can be to find the ideal position to attack the player from, or to find the nearest health pickup point. It is important to note that the environment query system is a plugin and must be enabled in order to access it within the editor. Environment queries are a powerful tool for developers. Each query can be tailored to a scenario in mind. An environment query is made up of generators, tests, and contexts to provide a desired result. We will actually discuss each of these in turn in the next following slides. Environment queries can be called from within the behavior tree, but can actually also be called outside of behavior trees entirely. So although we are discussing environment queries in the context of AI, it is important to know that we can make use of the system to drive other gameplay systems in our games. In the image on the left, we can see that we can create an environment query much in the same way that we can create our behavior tree or Blackboard asset. The image on the right shows us what an environment query looks like within the editor content browser. So let's take a look at how we go about creating our own environment query. It is only natural that we first begin with the generator. Now, generators are key to the genetic makeup of our EQS. Generators are used to produce an array of locations or actors. These are often referred to as items within the EQS system. These items can be tested and weighted. There are different types of generators already offered within Unreal. A small example of these are a generator that will get you all actors of a class, as well as a generator that can generate a set of points either in a circle shape, a grid, or a donut. If you wish to know more of the details about these and other generators are already offered in Unreal, then we can leave a link to the documentation. So now that we know that we can use a generator to essentially give us a set of actors or locations known as our items, this isn't very useful to us overall. A generator alone is not actually capable of doing such a task without the use of contexts. A generator on its own has no frame of reference whatsoever to the world or anything else around it. Environment contexts give generators and even our tests a frame of reference to use. A context can range from something simple as the querier to more complex contexts that we may think of. Context can be set up to return one or many items. It is important to know what generator you're using and pairing it with the appropriate context. Not all generators are built to deal with multiple items returned, for example. On top of context already provided by the Unreal Engine, we can also create our own set of context within Blueprint or C++. So we can recap what we know so far. We can use generators to create a choice of items, and we can give it context that give us a reference to use to generate those items. So whilst using these two in conjunction will give us a result, we can make use of tests to then better refine that result. Tests can be performed to determine which item is the best option available to us. And whatever that is can be tweaked to meet your requirements. Now, Unreal already offers a range of tests that we can make use of. So for example, we can make use of a distance test, a dot product test, a trace test, and even an overlap test. However, if these tests do not meet your requirements, then custom tests can be added. However, there is a caveat to this in that they can only be created within C++. We can attach multiple of these tests to a generator to essentially give us our best item result. So as can be seen in the image here, there are some common properties of tests that we can actually discuss. The first of this is the test purpose. And now this basically defines what our test aims to do. Whether it is to filter the items, or score the items, or actually even a combination of the two that we can see here on the screen. It's important to note that in the cases of filtering and score option, filtering will be done before we actually score those items. This is essentially to avoid calculating the score on items that will then be filtered out. Each test will expose a different set of properties available to us. So for example, if, and this is specifically true if we select filter or filter and score. In the example above, we have used a distance test. We use it as a test, which we basically use to filter out any items that are further away than our desired threshold. With scoring, we follow a similar pattern. If the score or filter and score test purpose is selected, we then get to decide how our items are scored. Again, the scoring properties will vary depending on the test that you have selected. In the example above, we can see that we define the points further away from the querier, that in our case, it can be the AI agent, will be weighed heavier than points closer to the querier. However, if we wish to flip this, we could do so in two ways, actually. The first is that we could achieve that flip of the scoring is just essentially change the scoring equation from being linear to an inverse linear option. The second way in which we could achieve this is by leaving the scoring equation as linear, but just alter the scoring factor to now be a -1. It's highly recommended that you place your filtering tests ahead of your score tests, so the calculations only take place on valid items. However, Unreal actually already takes care of this for you. However, I do also always recommend that any developer still does this, as it actually makes our tests more human readable to other developers. Unreal offers a great choice of tests that we can leverage to achieve our goals. So if they don't meet your requirements, you can always write your own tests within C++. So moving on to AI perception. The AI perception framework gives us developers the tools to gather sensory data for each AI. As can be seen here, Unreal gives us a certain access to stimuli, such as, for example, sight, hearing, touch, damage, and even a team sense. However, this is another system that does not come by default when creating our AI. In order to leverage this, we will need to do some extra steps. The first of which is to add an AI perception component to our AI controller. Once again, this can be done via Blueprint, as the AI perception component is a Blueprint spawnable component. Or we can also do this through C++. It is the job of the AI perception component to receive sensory data. It uses that information to then inform us of what has been perceived and by what sense it has been perceived by. What we do with this data is completely up to us. As discussed earlier, one of the key functions that the AI perception component makes use of is the actor's perception updated in the AI controller. A handy aspect of the AI perception framework is that it's totally customizable per AI and can be altered at runtime. The AI perception component can be added to the AI controller, like I said, through either Blueprint or C++. It will then allow us to define what sensors our AI will actually listen out for. We can actually also configure those parameters for those sensors. We can also define a dominant sense that will take precedence over all other sensors. It is important to note that this sense must be one of the sensors configured in the list of sensors configs that we have available to us. Otherwise, we can just leave it as none if we don't want a dominant sense. The perception component also exposes our events to Blueprint that we can utilize to drive that functionality. The list of events can be seen on the right-hand side. As an example, the onPrecision updated function will be fired when the perception component processes all of that stimuli and will return us that list of perceived actors. The AI simulus, the AI site simulus, does exactly what you would expect. It basically allows our AI agent to see things in the environment. The AI site config exposes key variables to developers that allows us to control what an AI agent can see. When an actor enters the site radius of the AI agent, the perception system will signal an update and pass through the actor that has been seen. We can actually go through some of these properties and that we can see in the image above. The first of this is the implementation. This is basically the AI sense class that we wish to use, and it just defaults to the AI sense underscore site. You can override this with your own implementation if you wish to do so. Next, we also have the site radius, and this is basically the max distance of which this AI, this sense can start perceiving actors. We also have a loose site radius, and this is basically the maximum distance over which a seen target is no longer perceived by the sense. We also have a peripheral version half angle degrees. It's quite a mouthful, but it's basically we'll decide how far to the side our AI can see in degrees. This angle is essentially measured in relation to the current forward vector of our AI agent. We also have a detection by affiliation, and this basically determines if enemies, neutrals, or friendlies can trigger the sense. We also have the auto success range from last seen location. Yeah, another mouthful. But when we put this value to something greater than 0, the AI agent will always be able to see that target has been seen as long as they are within the specified range. Lastly, we also have a max age. And this basically determines the duration which the stimuli generated by the sense can then become forgotten by the AI. If we leave this as 0, then this means that once we've registered the stimuli, it can never then be forgotten. Next, we also have the hearing stimulus. The AI hearing sense can be used to detect sounds generated by a report noise event. An example of this can be footfalls from the player or a gun being fired. So we can take a look at the values that we can then tweak here to drive our hearing sense. Again, is the implementation option, which can then is just a class that we use. Again, this is overridable by us developers if we wish to have a different implementation. Next is the hearing range. And this distance is this basically the distance in which this sense can be perceived by that perception component. We also have a line of sight hearing range, and this can be used to display different radiuses in the debugger when for the hearing range property. Again, we also have a detection by affiliation option here, which we can then determine if only our enemies trigger the sense, or neutrals and friendlies can also trigger the sense. Again, the max age is the same as before. It determines the duration in which the stimuli generated by the sense becomes forgotten, with 0 being never. Next, we also have our damage sense. If we want our AI agents to react to damage being taken, such as, for example, point or radial damage, then this is the sense for us. we have the implementation again as an option, and this basically controls how damage events are handled. However, if you wish to have your own damage system, then this is highly recommended for you to make your own implementation. Again, we also have a max age option here that works the same as before. So at this point, you more likely have noticed that we cannot control detection by affiliation, as this property is only exposed out to sight and hearing sensors in the engine. So next, we also have the touch sense. And this sense basically gives us the ability to detect when an AI agent bumps into something or when something bumps into the AI agent. A great example for this would be to allow our AI agent to have knowledge of the player if they bump into them as they're sneaking around our levels. Again, we have a similar array of properties that should be familiar to us that we have seen in previous senses. And lastly, we also have a team sense. And this sense will basically notify the perception system when someone from the same team as our AI agent is nearby. This can be useful in situations where we want our AI agent to react to its allies gathering around them, maybe to perform some sort of group attack. Once again, we could see very much of the same set of properties that we have already discussed. So at this point, we can now, so at this point, we can basically configure our AI agent to have a perception component and even give it the senses that we want to use to gather that information. There is still a last crucial part to the system that we need to talk about, and that is our stimulus source component. This component gives the owning actor a way to automatically register itself as a stimulus source. This component can be added through Blueprint or C++. With this component, we can dictate what sensors we register ourselves for, or by simply entering each sense into the register as source for sensors array that is exposed out in the editor panel. So now that we've covered how our AI can sense the world around them, we can discuss how we can tailor an environment that can give them objects to interact with. This is a new system added in Unreal Engine 5 called the Smart Object System. So what are smart objects? As the name suggests, they are objects placed in the world that both our AI agents and players can interact with. These objects contain all of the necessary information to handle the interaction logic for that object. Smart objects are part of a global database of smart objects, and they use partitioning logic. This basically means that they can be queried at runtime using things such as, for example, a location as a seed. One of the key advantages of this system is that it also uses a reservation system. This means that our AI agents or players can be aware of in-use smart objects around them. And this basically will also avoid multiple AI choosing an exact object to go and use. Smart objects have their own subsystem that keeps track of all smart objects in the level. This subsystem is created automatically in the level whenever the smart object plugin is enabled. It's worth noting that only one smart object subsystem can exist at one time. However, it is worth noting that in multiplayer games, the smart object subsystem is only actually instantiated on the server or the authority machine. As we can see in the picture at the bottom, the smart object subsystem is used to query for and return smart objects, and it is essentially a cache for our AI to bounce off of. If you're interested in how this is done, we can leave a link to the documentation, or you can search for it yourselves. It's written by the guys at Epic that describes the process in a great detail. The Smart Object Collection contains a list of smart object components associated within the level. The collection holds all shared configurations and is used to create all runtime instances of the smart objects to enable an efficient large world simulation outside of loaded areas. Again, there is only one smart object collection per level. So now that we know what smart objects are and how their back-end system works, how do we actually go about creating a smart object of our own? That's actually where the smart object component comes in. Um, the smart object component can be added to any actor and thus convert it over to a smart object. This will be then picked up automatically by the smart object subsystem and registered to that subsystem. This component sets up and stores a configuration of a given smart object template. This component still adheres to the world partitioning logic, so an actor holding the component can still be loaded and unloaded, whether we use world partitioning or level streaming. If the actor holding this component is spawned at runtime, then it will not remain in memory once it has been unloaded. The smart object definition is a data structure that contains immutable data that is shared between multiple instances of that smart object. This definition stores filtering information such as user-required tags, descriptive tags, and the default set of behaviors to execute on interaction. It also exposes one or more available slots that can be used by our AI agents or players. Each of these slots contain the following information: the location of that slot, the rotation of that slot that is relative always to the parent anchor. These are both the location and rotation is worth noting that they are baked inside the editor placement. They also have control over the specific behavior that can override the default one inside the smart object itself. It also has a list of gameplay tags as well as a user tags collection, and also runtime tags inside the slot itself. Lastly, we also come to the smart object behavior definitions. Now, these definitions essentially contain data needed by the AI agent or the player for a given interaction. Some common behavior examples are a gameplay behavior that can be used by a pawn or actor to perform that behavior. A player behavior, which is specifically being built for the player character. And also a mass entity behavior. This is basically behavior that makes use of the smart object behavior definition to configure the smart object that can be then used by mass entity rather than the usual gameplay behavior of an actor pawn architecture. Gameplay behaviors can also be implemented directly through Blueprint, so they're not code only. Now, moving on to another new addition to UE5, and this is the state tree. So what is a state tree? In short, they're general purpose hierarchical state machines. They combine selectors from behavior trees with states and transitions that are usually seen in state machines. States are arranged in a tree structure, and these states can contain evaluators, tasks, and transitions, which we'll discuss shortly. A selection of states can be triggered at any location inside the tree, but it usually starts off from the root of the tree. In order to create a state tree, however, you must first select the schema for your state tree. The current schemas available are a mass state tree or a state tree component. So let's take a look at the anatomy of a state tree. First of all, we have the root. This is basically the first state selected when the state tree starts running. Denoted by the number 2 there, we have a selector state. And this basically refers to a state that has child states within it. This state will never be selected directly, and selection will continue to one of its child states instead. Now, denoted by 3 is the state enter condition. This basically refers to a list of conditions that determine whether the state can be selected or not. Next, we also have, denoted by 4, a set of tasks within that state. And this basically refers to the set of actions that belong to that state and are executed when that state itself becomes active. For example, in the case of a flee state, we will first find a target a safe target to move to, and then we will move to it whilst fleeing and looking at it. Next, we also have transitions, denoted by the number 5, and this basically defines the conditions that trigger the state selection process. A transition is triggered when a task within that state completes, succeeds, or even fails, or even actually when a monitored condition succeeds. Now, a state contains a list of conditions which must be met in order to consider that state for activation. During the selection process, each state's conditions are evaluated. If they pass the selection process, then that proceeds to the child states if there are any. If there are no child states, then this is the state that would be activated. Each state consists of evaluators, tasks, and transitions. The data inside the state tree flows from the root to its leaves. This basically means that data can be exposed to any state that is available further down the tree. It is important to note that when a state is selected, it will activate all of the other states from the root to the leaf state. All tasks are executed for all active states, starting from the root down to the selected state. A state can contain multiple tasks that are all run concurrently for as long as the state remains active. So moving on, we also have tasks. And task in a state tree is similar to the concept of tasks inside behavior trees. A task is essentially just an action that is executed when its owning state is active. It can provide output to the state tree, and some common examples of that, for example, can be the selection of a target or even playing an animation. All tasks for a state will run concurrently. So once the first completes, it can then trigger that transition within the state, which can then result in the selection of a new state. States, sorry. Next, we also have global tasks. And global tasks essentially provide a way to run regular tasks that are associated with a specific state tree in itself, rather than a specific state within that state tree. These tasks can contain variables that and can execute custom code when the tree starts, ends, and ticks. Gathered data can then be used during the state selection and will be made available, as the name suggests, globally to the entire state tree. For example, we could have a global task that determines the current time of day. Since the global tasks are started before the root state in the tree, this information will be made available when the tree starts and during this the first state selection. If the state tree was controlling an AI, the state selection could result in a different behavior during nighttime versus daytime, for example. Next, we also have transitions. These are pretty self-explanatory. It can point to another state in the tree, which will then trigger that state selection process again. A transition can contain trigger conditions needed to be met before that transition even triggers itself. Transitions are evaluated starting from the leaf state and progressing upwards through to the root. During this process, the first transition that succeeds will lead to and leads to a state selection is going to be the one that's triggered. This hierarchy allows for grouping of common transitions if we want to do so. Completion transitions, however, now trigger at the state where the task itself was completed. So if its execution is currently at the root, guard, or leaf state, and a task at the guard state completes, then the transitions on the guard and root are handled, and we will actually just skip the leaf state. It's also important to note that the tick and event triggered transitions will have precedence over completion transitions. Another new feature to U5 is the mass entity framework. And this is essentially a framework for data-oriented calculations. A math entity's primary data structure is the fragment. And a fragment is a data-only element, and it represents an atomic piece of data that can be used for calculations. Examples of fragments, for example, can be things such as a transform or even the velocity of our AI. It is important to know that fragments cannot be created inside Blueprint. Now, these fragments can be grouped together into a collection, and these collections can then be associated to an ID. The collection of fragments is actually called an entity. Now, the ID associated with the entity can then be used for lookups. Creating an entity is similar to class instancing an object in object-oriented programming. However, instead of strictly declaring a class and its functionality, entities are built by fragment composition. An example of the entity is that we can take those two fragments that we discussed before, that being our transform and our velocity. These two fragments now form our entity, and it will be given a unique ID. Again, it is important to note that entities are data-only elements, so they have no logic inside of them. Moving one step further, we have archetypes. Now, archetypes are a collection of those entities that of an identical composition. Archetypes are composed of different types of fragments in a specific configuration. So if we take our previous example of an entity that's made up of our transform and velocity, we can build a collection of those entities that hold the same configuration, and that will give us our archetype. So let's take a look at some visualizations of an archetype. We can see here that we have an archetype that holds an entity made up of our transform and velocity fragments, as per the example that we've been discussing so far. So let's take a look at how archetypes are organized. Entities in an archetype are organized in memory chunks. This basically ensures the best performance when retrieving fragments associated with an entity of the same archetype from memory. Now, processors are stateless classes that supply the processing of logic for those fragments. It makes use of entity queries to specify which types of fragments they need to perform their operations on. For an example of a mass processor, we can take a look at the mass apply movement processor that's already inside the plugin. Now, entity queries provide batches of fragments to the processor without regard of the individual entity identifiers. As we can see here, we have an entity query that will return our processor two arrays of transforms and velocities, the exact makeup of our example entity that we've been using. Now, tags are just essentially are a trivial fragment that contains no data of its own. The existence or absence of tags can be used as data itself, and tags are a part of the entity's composition. We also have chunk fragments, and a chunk fragment is a fragment associated with a chunk instead of an entity. This can be used to store per chunk data used in managerial processing, such as, for example, levels of details calculations. And they are all part of an entity's composition. So last by no means least, we also have the zone graph, another new addition to UE5. Now, a zone graph was envisioned to be a lightweight navigation system that allowed for pathfinding even in non-streamed portions of the world, and also built for controller direction of navigation. The zone graph uses metadata to represent specific navigation flows, such as traffic lanes, sidewalks, wood trails, and so much more. This metadata is represented as point-to-point corridor structure connected by segments. In the next slides, we will cover briefly how you can define these corridor structures for yourselves. This system can be used for essentially efficient long-distance navigation where precise navigation is desired. For example, we can think of an AI driving around a city. Now, there's a few critical classes that we need to take a look at when defining our zone graph. The first of these is the zone shape. And zone shapes define the area and shape that the zone graph lane takes. Zone shapes can be configured with the lane profile, which determines the number of lanes, as well as tags and the direction and width of those lanes. We also have the zone graph data, and the zone graph data is a built navigation data for zone graphs similar to that of the recast actor that is present when using the nav mesh. Now, zone graph data is not built automatically whilst the user is editing. It is instead built on demand via the build section at the top of the editor, and then we can select the build zone graph option from the menu bar. However, you can enable automatic zone graph building by enabling the build zone graph while editing Boolean flag inside the project settings. We also have a zone graph testing actor, which is used for testing navigation if navigation is possible between two. Apologies. Sorry, let me repeat that. We also have the zone graph testing actor, which is used for testing if navigation is possible between two testing actors, similar to the traditional navigation testing actor that we can use with the recast nav mesh. A zone graph testing actor can be configured with a query filter, another zone graph testing actor to test the navigation between. An optional test can then be run when attempting to navigate. The testing actor can also show other debug information related to pathfinding, such as, for example, lane path, linked lanes, and smoothing as well. Lastly, we also have the zone graph annotation testing actor. And this actor essentially allows us for any number of tests to be run to simulate annotations at a specific point. Custom tests can be created to match the profile's specific needs as well. So to create a lane profile, we must simply do the following. We need to go to the project settings and open up the zone graph settings. We can then click the plus button to create a new lane profile. In the example that we see here above, we define a new profile and that we've named two-way traffic. We then add 2 lanes to this profile, both with a width of 150, and we define the direction for these lanes, one being forwards and one being backwards. And that's it. It's as simple as that. So before we wrap up, let's cover some developer and resources and support that we have available to us when using the Unreal Engine. So the first of these is the Unreal Engine documentation. This basically has a whole host of documentation on pretty much every part of the engine and is kept up to date by the guys at Epic. We also have the Unreal Engine YouTube channel and Twitch stream. These have live training videos, conferences, tips and tricks, and so much more. Next, we also have the Unreal Developer Network, or the UDN. And this is basically a dedicated Unreal Engine support community available to licensees. You can browse articles and view other questions, and answers are provided by Epic staff or other licensees on the website. We also have the Unreal Engine 5 Answer Hub. This is a public version of the UDN where most answers are provided by other members. So it's worth keeping in mind that they may not always provide the correct or most optimal solution to your problem. Epic do keep an eye on these questions and will sometimes provide responses themselves. It's a really good place if you want to go get a quick answer. Lastly, it's also worth mentioning that there is an Unreal Engine community wiki, and this has a whole host of tutorials and documentation from explaining what an actor is to a method for multi-threading. It is again community-led, so it may not always have the most optimal solutions, and some of them may actually be out of date. And with that, we've come to the end of our talk. Thank you so much for listening.
Can I just say a big thank you, Carlos, to yourself and to Dan as well for doing these courses this week. And thanks to all the people who support you at Flix. And I'd just like to thank everybody for coming along to these sessions. I'd encourage you to ask questions via the Question Pro and let us have any feedback as well. So thank you very much, everybody. And I just left to wish you all a lovely weekend.